Okay, hello. So today we're going to talk about separable equations, which are a lot like the autonomous equations that we talked about last time. So let me go into writing mode. Okay, so last time we found out that you had these special first order equations when your derivative was only had the independent variable in it, basically. And you could just solve this by integrating. So what about if we have something like this, like dy dx equals -6xy? So you look at this and you're like, okay, it's not just dependent upon the x variable. So it's not the special first order differential equation, but it is something called separable, and we'll see what we mean by that. So what you can end up doing is separating the different variables and their corresponding differentials to different sides of the equation. So for instance, we have a y over here, so let's multiply by 1 over y on both sides. And let's multiply by dx on both sides. Okay, so the y and the 1 over y cancel, the dx and the dx cancel, leaving you with dy over y equals minus 6x dx. Looking at this, this is something that you can integrate and solve. So you're like, okay, let's integrate. Okay, on the left-hand side, dy over y is going to be the natural log of the absolute value of y. On the right-hand side, you're going to get minus 6 over 2x squared plus c. So let's simplify that. You get natural log absolute value y equals -3x squared plus c. Now remember, we're solving for y, so you can raise e to that. Our previous equation will be the exponents. So you get y of x equals e to the minus 3x squared plus c. Now, you might remember the rules of exponentials. This is e to the minus 3x squared e to the c. E to the c is just some constant, which we can now just write as a. So you get a e to the minus 3x squared plus c. That is our general solution. You could find out what the a, oops, I'm sorry. Sorry, it's a times e to the minus 3x squared. You can now find the constant a, or we call this the implicit general solution. You can find the a, the constant, by an initial condition. For instance, if you were told that y of 0 equals 7, you could plug this in. Y of 0 equals a e to the minus 3 times 0 squared equals 7. That's going to be e to the 1. Your a would be 7. And then what would be your particular solution? Y of x would be 7 e to the minus 3x squared. That would be your general solution for this initial condition. Okay, so there's a particular class of differential equations that we call separable. So what are separable differential equations? Well, basically it's something like this. You have dy dx equals f of xy. Okay, so what you need to be able to do is separate your f of xy into two different parts. A part which is called g, which depends upon just x, and k, which just depends upon y. If you can rewrite your function as a product of two other functions which only depend upon one variable each, you can now separate them. How do you do this? Well, you divide both sides by ky, and you get dy over k of y equals g of x dx. You will now be able to integrate this. Notice on the left hand side, you're always going to end up with a what's it called? Some sort of exponential. Although usually we write 1 over k of y as h of y, so that we can have this as h of y dy equals g of x dx. Looks nicer. So obviously this only works assuming that that you don't divide by 0 anywhere, right? You don't want that k of y to be equal to 0. Okay, so let's do another example of this. So let's solve dy dx equals 4 minus 2x over 3y squared minus 5. Okay, so can you rewrite this as your g of x and your k of y? Yes, my g of x would be 4 minus 2x, and my k of y is going to be 1 over 3y squared minus 5. You multiply those two together and you get what you want, which means that my h of y is just going to be 3y squared minus 5, right? So what you get is 3y squared minus 5 dy equals 4 minus 2x dx. And you integrate, leaving you with y cubed minus 5y equals 4x minus x squared. Okay. And this gives you an implicit solution, notice. The graphs of these look really weird, so I'm going to go over to Wolfram and we're going to show you what those look like. So you get like some really weird graphs. So bear with me a moment while I change my screen to Wolfram. There we go. Okay, so let's use a stream plot. Okay, so remember you want 1 comma what your dy dx is. So your dy dx in this case was 4 minus 2 times x divided by 3 times y squared minus 5. Okay, let's have our x values go from negative 10 to 10. Let's have our y values also go from negative 10 to 10. Okay, so you get this weird swirly plot. We're going to center this. Let's have our x go a little further over 15. There we go. So now it's a little more centered. So looking at this, you get this like weird sort of keyhole here. And we're going to talk about what's going on. So let's copy that graphic and we're going to switch back over. So 1 second while I paste the graphic over so we can analyze it. And we'll return. Okay, cool. So you can sort of see when you look at this, there's like this vortex around here. You can like see these like swirls. There's like the symmetry through right about here. Now let's talk about why that's going to be. So what do you know about this derivative? You know that 3y squared minus 5 can't be equal to 0, correct? Which means that 3y squared can't be equal to 5, which means that y squared can't be equal to 5/3, which means that y cannot be equal to the square root of 5/3. Now if I go over to Wolfram and I calculate, hey, what is the square root of 5/3 as a decimal, that gives me approximately 1.29, in other words 1.3. And looking at this, you can see, or sorry, y equals 1.3. 1.3 is about right here. And if you draw a line through it, you can actually see, actually, let's do a different version of this. Let's do this a vector plot. 1 second. I want to make sure I say this right. Ah, yes. Okay, there we go. So what you find out is that the solution curves, they are split into two parts. One part that is above y equals square root of 5/3, and one part that's below square root of 5/3. So for instance, let's choose this point right here. The solution curve follows it, and it looks like this. But if you were to choose a point below that point, or let's say right here, this would be your solution curve. Or if you choose this point right here, this would be your solution curve. So if you were to start off above y equals 5/3, you can only get this part of the graph in red. You cannot continue to this part over here. Why? Because, well, the derivative would be undefined there. So you actually get two different possible solutions. A part that gets cut in the part above, and a part that gets put into the part below. Okay? So you have to be aware of this. So no solution can cross that line, basically. It also works for negative 5/3. It also works for y equals... What was that? Y equals minus square root of 5/3. So you actually can sort of see there's this like gap right here. Oh, so I should have done this a little better. So really, if you're on this point right here, you only get this. But you could be on this point right here and get that. Likewise, if you're at that point right there, you get this part. If you're over here, you only get that part. Or if you're up here, you only get that. If you were to look at the graph, you would see that you get these cool, interesting keyholes. Like, you see how it looks sort of like a keyhole, like it goes like that, and it looks like there's a place to put a key. But because the derivative ends up being undefined, you actually get three sections. Sorry, not two. I forgot about the fact that you have negative square root 5/3. Okay, so you get three different parts. So you're sectioned into these different areas there. And this becomes apparent because you know that the derivative would be undefined when y equals 0. You know from the beginning. And that's like what I said earlier. When you rewrite this, you can't ever divide by 0. Okay, but separable equations are pretty straightforward to solve. You can separate them. Okay. And this leads us into our final example. And we will look at it. Which is the growth equation. Okay, so let's say you have that the derivative of x with respect to time is proportional to the value of x. So the change in x is proportional to the value of x. This is actually a separable equation. You can divide both sides by x, and you get dx over x equals k dt. You can integrate. Integrating dx over x is the natural log of the absolute value of x. Integrating kt will be, or k dt, my bad, is going to be kt plus c, and this is going to be very similar to what we had happen last time. Well, that's, if you raise exponentials to those, on the left-hand side, you get x of t, and on the right-hand side, you get e kt e to the c, which is a e to the kt. Right, and this is the exponential growth equation. Right, exponential growth happens or occurs when your growth rate is proportional to the size of your population. Very related to this is Newton's law of cooling, which looks very similar. Well, if the rate of change in temperature with respect to time is proportional to the difference between the ambient temperature and the temperature, you can separate these. dt over a minus t. It's going to give you k dt. On the right-hand side, you get kt plus c. Now on the left-hand side, you could do a u substitution. U will be equal to a minus big T, which means du equals minus dt, which means you get minus du over u, which means you get minus natural log u, kt plus c. And we can discharge the u. This is minus natural log a minus t equals kt plus c. When you raise the exponential to that, you get something very similar again. E to the c will just be a, e to the kt. And then I guess you could just switch the minus to the other side. Let's put it over here so you get a minus kt. So over here you get a minus t equals, actually we should use this as something else. We shouldn't call this a because we have another a here. Let's call it, let's just call it c. So your temperature. So if you subtract over, you can get minus a, but when you, so let's do minus t equals ce minus kt minus a, which means the temperature equals the ambient temperature minus ce to the minus kt. Boom. Very similar. So with Newton's law of cooling, if the rate of cooling is proportional to the difference of these two temperatures, you get something that looks a lot like exponential decay. Okay, and these are very, very common. They show up a lot. They are separable equations. They're rather easy to solve. And that is the end of our 1-4 video.